want to warm our flat by extracting the heat in our warm beer and pumping it into the room using the refrigeration cycle as shown here. We want our kitchen to be 5 degrees warmer and our beer to be the perfect drinking temperature of 1.6 degrees Celsius.
The temperature of the condenser must be greater by at least 5 degrees Celsius than the temperature of the room. Therefore, the temperature of the condenser equals 40 degrees Celsius.
To analyse the refrigeration cycle, energy balance is needed to be performed over the condenser, throttling valve, evaporator and compressor. The change in enthalpy over each of these components equals the heat and work inputs. The condenser is isobaric, and using the temperature equals 40 degrees Celsius, the pressure at the liquid saturation line on the molar diagram and the enthalpy can be found.
The throttling valve is adiabatic and isobaric, therefore the change in enthalpy over it is 0 and H2 equals H1.
The evaporator is isobaric, and using the temperature equals negative 10 degrees Celsius, the pressure at the vapor saturation line and enthalpy can be found on the molar diagram.
The compressor is adiabatic. To determine the reversible work, constant entropy over the compressor is assumed. Using the efficiency of the compressor of 70%, the irreversible work is found, and then QH, the heat released by the fridge, can be found.
The energy required to heat the room was determined as 441 kilojoules. The fridge was assumed to be working at its maximum power rating of 150 watts. Work of the fridge equals the irreversible work found for the compressor. These were used to find the mass flow rate of the coolant and hence the flow rate of the heat to the room from the fridge.
Therefore, it will take 15 minutes to heat the room by 5 degrees Celsius by transferring the heat from a fridge full of warm beers. A warmer flat and cold beers makes happy students.